Hello and welcome to this lecture of elements of mechanical vibration. The topic which we covered last lecture was on the energy based methods. So, today's lecture is devoted to exploring how the geared rotors are modeled in a vibratory system, and also we will get a brief introduction to how the response to transient excitation can be obtained. So, you would all agree that there is a great possibility of we encountering a gearbox in a powertrain, a typical powertrain in a mechanical engineering system, and therefore, it would be interesting to understand how the gearbox is modeled as a part of the vibratory system. And today's discussion is going to focus on how do I account for a gearbox or a gear pair in a vibratory system. So, for that example, I would like to consider is that of a wind turbine, and the picture that you see here is a simplified wind turbine model, where the rotor blades under the influence of the flowing wind basically would generate a rotational motion to the bladed rotor, and this particular shaft is called as the low speed shaft. This is the typical low speed shaft which is directly connecting the blades, and that goes as an input to the gearbox that you see here. The green colored one is essentially a gearbox. The gearbox there has a function of stepping up the speed, and the output of that gearbox goes as an input to the generator. So, basically you have a wind turbine input shaft to the gearbox, which could be a simple single stage gearbox. As an example, one may consider this, and the output from the gearbox is a high speed rotating shaft, and that goes as an input to the generator here. Okay. Obviously, the rotational speed at the input is quite on a lower side, because of the wind cannot impart sufficient energy to increase the speed, a higher speed of rotation. So, this, as I said, is typically low speed shaft, and then through the gearbox you step up, and then the speed here is going to be much higher. So, this is called as the high speed shaft here. That is how the configuration in general as a simplified system is going to look like. The generator of course generates electricity, and this particular picture basically shows how the power is actually transmitted. Getting the input wind power or wind energy getting converted into an electric energy, it happens through this kind of a mechanical powertrain. So, the question now here for us is to convert this entire system into a simplified vibratory model as a part of the vibration analysis process. Now, we know that a physical system, as you see here, which we are discussing, this physical system need to be converted into a simplified vibratory model. Now, we are going into finer details. For example, in the initial lectures what we saw is that this entire nacelle which is sitting at the top of this vertical column or a tower, we treated this to be a simple single degree of freedom system, is not it? Now, as an overall system, this is fine to start with. Now, what we are doing is we are focusing on the mechanical system within nacelle, and the system here is going to be a torsional vibratory system, and so this becomes a global vibratory system, that within that this itself, the mechanical system within the nacelle itself is now going to be another local level vibratory system, which is basically a powertrain. Now, so the problem here in terms of now some of the parameter details is is posed here in the form of a problem. And so, what we are seeing here is a question related to wind turbine vibratory model development. It says that this wind turbine drives the generator through a gearbox with the speed ratio of 1:4, which means that if the low speed shaft spins at 1 unit rotational speed, the speed here at the output of the gearbox is going to be 4 units. Okay. So, 1 RPM stepped up to 4 RPM, that is the gear ratio. The mass moment of inertia of the generator moving parts is 90 kg square meter, and that of the blade assembly is 540 kg square meter. The pinion and gear possesses the mass moment of inertia comparatively almost negligible values, as you can see. Okay. The shaft supporting the blades is 5 meter long, and its diameter as 30 centimeter. Generator shaft is 50 centimeter long with a diameter of 15 centimeter, and with that you have to make a model and find the natural frequencies of the system. So, so with that we focus on this torsional vibratory system, and this is the simplified model that I have of the system in question. So, this rotor blade assembly is what comprises this wind turbine inertia. This shaft, which is an output from the wind turbine, is this shaft that we have shown here. The dimensions are as per the given data in the problem. That is giving an input to the gearbox. So, this is our gearbox having a step up gear pair, where the generator is spinning 4 times the speed of the wind turbine, and of course, the generator is connected through a shaft. The dimensions are given here, and the generator of course then generates electricity. Now, the rest of that part is not a mechanical system. So, we will focus on this simplified vibratory model. Okay. Now, because there will be varying torque as an input to the wind turbine, the wind load is going to be fluctuating, there will be torque fluctuations, and that would set up this entire system into torsional vibrations. Now, with this let us look at how many degrees of freedom would this system typically will have. Now, there are as many number of discrete mass elements, the number of degrees of freedom are expected to be in proportion. Obviously, you have a huge inertia for the wind turbine, which are all given here. So, wind turbine has 540 kg square meter, and the generator has 90 kg square meter. In comparison, if you see the gear and the pinion has much smaller one, the inertia. So, we as a part of our approximation can neglect the inertias of the gear and the pinion. Okay. So, what it then boils down to is you have a generator, and then that is connected through this gear pair to the turbine, and both of these inertias are sizable. So, I can then, as our approximation process, can have generator inertia. Maybe I will I'll write this as G, that is the generator inertia, and this generate the turbine inertias. Now, here is the catch, the inertias of the gear and the pinion being minuscule as compared to that of the generator and turbine. We can neglect the inertias, and then what we are left with is obviously there would be 1 degree of freedom corresponding to the generator, and there would be the second degree of freedom corresponding to the turbine. Okay. The question now is, how do I take care of the gear pair? Now, obviously, you all know that there would be a sudden step change in the twist angle of twist at this point, and the angle of twist at this point because of the gear ratio. Okay. The speed of rotation of the generator is going to be 4 times that of the turbine, and now if I want to further simplify this into a 2 mass model, we already have decided that it is going to be a 2 degree of freedom system. We cannot neglect the generator mass or generator inertia and turbine inertia. So, you have to have 2 degrees of freedom, and therefore, this 2 mass system. So, you have turbine and generator. What do we do with this gearbox which is here at this point? Okay. The end of the turbine shaft has a gearing connection. Okay. Now, when we try and simplify this or transform this to a simple 2 inertia system with a connecting shaft which has its own torsional stiffness now, we need to account for the fact that the energy associated with this part of the train should be appropriately accounted for when we convert this model into a 2 mass model like this. Okay. An obvious way of doing it is going to make sure that the total energy of vibratory system remains the same as it was here. The same energy must be retained when we convert that into a 2 mass model with a connecting shaft. All right. So, it is quite obvious that we can now consider that the turbine and its corresponding shaft which is given here, maybe including the gear, is taken as a reference part of the system of this gear powertrain. So, this turbine rotational speed and the degree of freedom corresponding to it is now fixed to theta t, and now look at how this particular shaft which is connecting the generator to the pinion, which is basically this particular part of the shaft, when you align or connect it directly to the turbine, obviously the corresponding twist is going to be remaining the same, and basically the strain energy associated with the twisting of the generator shaft here should be scaled, so that when the strain energy is stored into this shaft when it is directly connected with the turbine must be the same as it was when the generator was connected to pinion, and then there was a step up of the twist from the turbine or from the gear to the pinion. Okay. On similar lines, when you connect in this simplified model the generator inertia directly to the turbine shaft, the kinetic energy associated with the rotation of this generator should be the same as it was when the generator was connected through the gear pair, and obviously we know that the generator was spinning with a higher speed. So, earlier kinetic energy of this generator should be retained when we connect it directly to the turbine. So, what is happening here is that the generator along with its shaft, when it is directly coupled with the turbine shaft, the original strain and kinetic energies of the generator and the shaft associated with it should be scaled now, so that the total energy of the system remains the same. Okay. And that is what our purpose of discussion today is, that how do I replace the gear pair and connect the two inertias together, retaining the original kinetic and strain energies. So, what we do is we scale the torsional stiffness of this shaft. So, earlier supposing that this shaft has torsional stiffness of kg, but that torsional stiffness was corresponding to the shaft which was subjected to a different twist as compared to when it is connected to directly connected to the turbine. So, I will have to scale this torsional stiffness to some kind of an equivalent torsional stiffness, and so that the total strain energy stored is the same when the movement of this shaft is going to be in line with that of the turbine. On similar lines, this generator inertia also will have to be scaled, so that the generator inertia is scaled so that the new generator inertia will have the kinetic energy similar to what it had when the gear pair was a part of the system. Okay. So, both the original generator inertia should be scaled to equivalent generator inertia, and the original generator shaft torsional stiffness should be now scaled to a new value of generator shaft torsional stiffness. So, after we do that scaling and come up with an equivalent inertia and equivalent stiffness, so that the total energy of this simplified system is the same as the original system, then we have achieved the modeling process properly. So, the equivalent system, what we are going to do is, as I mentioned, we will bring the generator and its gearbox and the shaft along the line of the wind turbine, so that it can rotate at the same speed as that of the wind turbine. Now, if that happens, as we discussed, this part of the system remains the same. So, the wind turbine inertia remains the same as original one, and the stiffness of the wind turbine shaft remains the same, because the gearbox is somewhere here. Okay. So, beyond that there was a step change in the property, and that is how we are going to see how that can be obtained. For example, the inertia has to be modified, and therefore, what we are saying is half of the equivalent generator inertia times square of the turbine speed, because now they are all connected directly to the wind turbine. So, whatever is the speed with which the wind turbine rotates, the same speed will be with for the generator. If that happens, then the inertia of the generator cannot be the original, it has to be changed. But the kinetic energy associated with this should be same as the original kinetic energy, and original system had this inertia of the generator. It rotated at this speed omega generator. The generator will have a higher speed of rotation as compared to the wind turbine, because of the step up gearbox with the speed ratio of 1:4, and so the whole premise is that in both cases the kinetic energy should not change, obviously. So, if that happens, this equivalence will finally give us the value of the equivalent generator inertia that we can use in this particular configuration. So, using this expression, one can find what is the equivalent generator inertia based on the original generator inertia and the two speeds, that of the turbine and generator. On similar lines, the strain energy here will be based on the angle of twist that the generator experiences, but that angle of twist will be different compared to the angle of twist which is experienced in the turbine shaft. So, because of the step change at the gear, we need to again recalibrate the strain energy associated with this shaft, and for that the two strain energies again will have to be equal. So, the equivalent stiffness of the generator shaft, that is this one, half K equivalent generator times theta turbine square. So, that is the angular twist based on the turbine twist or the rotational speed, is going to be equal to the strain energy in the original shaft. So, the original shaft had the stiffness K generator, and theta generator is the angle of twist. So, the strain energy is now in this case is made equivalent, and from this you can find out the equivalent generator shaft stiffness. So, by equating these two you can find out both equivalent generator inertia and equivalent generator stiffness, and in both these two cases what we get is they are related through the gear ratio. So, whatever is the step up speed ratio that you have, that comes into the expression based on. So, obviously, if the speed ratio is 1, they will be almost same, because there is no change in the twist as well as speed of the inertias and the shaft. Once this is done, the rest of the things are quite straightforward. What is important in this example is how to treat a gear pair or a gear box in two coupled rotors in developing a vibratory model. Once that is done, then rest of the procedure is quite straightforward. Okay. So, once we got the equivalent generator inertia and equivalent stiffness of the generator shaft, which is this and this, we now have to find what is the stiffness of the entire shaft, okay, which connects the generator and turbine. All right. So, we know that these two, this shaft can be one spring, it is a torsional spring here, and then there is another spring here which is of representing the turbine shaft, and they are in series. So, you can find out the equivalent stiffness, and so it is possible to find equivalent stiffness in this particular case. 1 over K E is going to be equal to 1 over K generator equivalent stiffness plus 1 over K turbine. You can find this because the dimensions are given, the lengths are given, and you can assume shear modulus maybe 80 gigapascal or so, assuming a steel shaft. Whatever is the material, that shear modulus can be used to find out the value of the shaft of the turbine. So, G IP over L, and IP we all know pi over 32 d to the power 4 meter to the power 4 is the polar area moment of inertia. The length is given already because this part of the configuration is untouched. We have not disturbed this, or we have kept it as it is. So, the original length of the turbine shaft which is given to us will remain as this, and the shear modulus maybe 80 or 90 gigapascal can be taken, this value. So, this numerical estimation of KT is known. What do you need for K equivalent generator? You need K generator, that means the original configuration of the generator shaft's stiffness, that also you can get, because ultimately this generator shaft stiffness will also have the same expression, G IP over L. The length of the generator shaft was originally given in the configuration, the diameter was also given. So, this value can be easily obtained. So, when both these two individual stiffness elements are known, you can find out K E numerically. Okay. So, when you have the total 2 mass system as we see here, the equivalent stiffness of this total shaft, assuming this to be one spring and another spring in series, K E can be numerically obtained. So, we assume that we know this K E numerically, I mean its numeric value is completely known. J1 E is basically the generator inertia, J2 in this case is the turbine inertia, they are coupled together, and now these two shafts these two inertias are like connected by a single shaft like this, right, and they are going to rotate. They will be held in bearings, so they will be free to rotate in the bearing supports. Now, they would have two possible motions. One, in this case both of them will simply roll like together. Okay. Now, this is a 2 degree of freedom system, 2 mass system. So, the detailed analysis of more than 1 degrees of freedom we have not yet touched, but I shall give you or we are going to solve this because this system is very peculiar one, in the sense that as a rule we know that if there is 1 degree of freedom, there is 1 natural frequency. If there are 2 degrees of freedom, there will be 2 natural frequencies of the system. But this is a peculiar system in which the first of the 2 natural frequencies will be 0. Why? Because both the rotors or both these inertias rotate together like a rigid body, okay, or there is no stretch in the shaft connecting these 2 rigid bodies. Okay. So, the fundamental natural frequency or the first of the 2 natural frequencies is 0, which actually means that there is no oscillation, there is a rigid body motion. Okay. So, that is what happens, that out of the 2 natural frequencies, at the first natural frequency which has a 0 numeric value, both the inertia simply rotate. So, you can imagine that the wheels on the axle or the entire axle itself is rolling, you know, without storing any strain energy, or the 2 bogies connected by a flexible spring, the 2 bogies are simply moving together without the intermediate coupling being stretched anyways, right. So, it is a rigid body motion. In the second natural frequency, these 2 inertias, they move in opposite direction. So, in this particular case, the motion now is going to be this mass moving in the counterclockwise sense and this one is in the clockwise sense. So, there is now going to be a twist and strain in the shaft. So, this shaft is going to be under torsional strain, shear strain, and then what will happen is that this disc is going to move counterclockwise when this is going to move clockwise, and after some time they will flip their direction. So, they will oscillate, keep on oscillating like this. And it so happens that we must, I mean, you all have studied in the basic solid mechanics or strength of material course that there is a location somewhere here along the length where the twist is maximum at the 2 ends and the twist gradually reduces to 0 here, and then the twist is negative in the opposite in the remaining part. Okay. So, about this particular point along the length, this part oscillates like one single body on one side and this part oscillates like another body in the opposite sense. So, both of them will oscillate with the same natural frequency, which is expected, otherwise it will not oscillate like harmonically. So, at the natural frequency, when entire system vibrates as one single unit with the same period of oscillation, what we now assume that there will be a location somewhere along the length of the shaft where there will be 0 twist and this body will oscillate in one direction and in the opposite direction this body will oscillate. Okay. So, essentially this part will act like a single degree of freedom system and this can be considered fixed, and this part oscillates like another single degree of freedom system. Both of them will have the same natural frequencies. Together they do still constitute a 2 degree of freedom or a 2 mass or a 2 inertia model, and our job is now to carry forward and figure out what is the expression for the natural frequency. These are all the conceptual discussion of how they will oscillate or vibrate, but it is sure that when they vibrate at its second natural frequency, there is going to be a location along the length of the shaft where the twist will be 0 and the left hand side disc will move in a direction opposite to the direction in which the right hand side disc oscillates. So, they are going to simply oscillate like this in opposite phase, which gives us a position of 0 displacement somewhere here. We do not know where exactly the node position or 0 displacement position is. So, what we do is we assume that the total length here is LE, the equivalent length of the total shaft. Now, mind you, this is a total shaft which embodies some part of this shaft corresponds to the original turbine shaft and the other remaining part is the generator shaft part, equivalent generator. So, we say that okay, total length is let us say LE and the position where the 0 displacement happens can be assumed equal to A times LE. That means, a fraction A is used to denote the position of this 0 displacement position. Similarly, 1 minus A times LE will be the remaining part obviously. So, A times LE is this part of the shaft and 1 minus A times LE is this part of the shaft. Okay, now, this stiffness, the stiffness of this spring and stiffness of this spring can be denoted as K1 and K2. Okay. And what will be K1? K1 will be G or C, whatever symbol that you use for shear modulus, IP into the length. Now, the length of this part of the shaft is already assumed as ALE. So, the length of this ALE is taken for denoting the stiffness of this part of the shaft. The remaining part of the shaft is K2. So, that spring has CIP upon 1 minus A times LE, the length of this part of the shaft. So, these are the two spring stiffnesses and we all know that the natural frequency of this system or this part of the system has to be identical to this, otherwise the position of the node will not be or the 0 displacement position will not be the same, exactly same irrespective of the time. So, each part has to oscillate with the same time period for this entire system to vibrate at the same natural frequency. So, it basically helps us to understand that the natural frequency of this half can be obtained by writing the expression that it is going to be square root of omega n is going to be square root of kT, the torsional stiffness upon the inertia, okay, of the disc. Now, for the left hand side half here, the torsional stiffness here is K1 as we have defined and J1E which is the equivalent generator inertia is the expression that we can use. Now, please make a note, we do not know the numerical value of K1 because we do not know where exactly this node is positioned. So, A is an unknown here, G IP over LE is already known because this KE is known numerically. So, this entire value actually is this entire value is known. So, what we can say is KE which is here is known numerically, which is CIP over LE is known. So, I can use IP over LE as KE over C. Okay. Now, KE is known, C is the material constant. So, I know the ratio IP over LE. So, this K1, okay, this K1 is C IP over A into LE and then 1 over J1E. Now, make a note here that if I replace IP over LE by this value, I will have all the parameters completely known numerically. So, C is known numerically, IP over LE I am going to replace as Kc over C. In fact, C will cancel out. A is the only unknown and 1 over J1E is also known completely. This is the natural frequency of this part. I will also find out natural frequency considering the second part. So, for that I will have this expression of C IP over LE, and then I have another term in the denominator, that is 1 minus A and then 1 over J2 or J turbine. So, in this case let us say if it is J2. So, in this case also except A, I have all other parameters known. So, in fact, if I replace IP over LE using this expression, then I will have here Ke, C will cancel out, and then I have 1 minus A and 1 over J2. So, this is omega n, same as this. Now, you may notice that from one expression I have square root of Ke over A into J1E, and from the second expression, which is this of the natural frequency, I have Ke over 1 minus A times J2, which is the turbine inertia. Now, if I equate this, Ke will simply cancel out, and J1 and J2 and J1E are numerically known. So, the only unknown, that is A, which I can find out from by equating these two. Once you find A, you can put it back into this equation to find out the natural frequency value. Okay. So, this is how the natural frequency of this two mass system, if it is such that the fundamental natural frequency is 0, the rigid body motion, can be obtained. But otherwise, we are going to discuss in general a two mass system separately once we are done with the single degree of freedom system. What is the most important takeaway in this case is how to reduce a geared rotor with a gearbox, which we discussed, these two rotating shafts, how you can model this like an equivalent system to be able to analyze this as a vibratory system. How to take care of the gearbox is something which is the most important part of the discussion in this particular case. Okay. All right. So, by equating this, you can find out A, and then you can find out the expression for the natural frequency. It is left to you as an exercise to show that the natural frequency of this system can be shown to be this, and that is a small exercise that you can always carry out. What is interesting here is to see that this natural frequency expression is like equivalent inertia. Okay. So, I will call this as an equivalent inertia. So, this is like two inertias in series. Okay. Just like two springs in series, we have an expression K1 K2 upon K1 plus K2, right. When the springs are in series, these two inertias are in series, and you can see that the expression or expression for the equivalent inertia turns out to be J1 J2 upon J1 plus J2, right. That you will get by making use of all the expressions that we have derived in the earlier part. Okay. So, with this we now move over to another most important topic in the single degree of freedom system analysis. After having discussed the free vibration response to initial excitation or initial disturbance, we shall now focus our attention on finding out the response of a simple vibratory system to a transient excitation, in the sense that in earlier case when this vehicle was subjected to some disturbance at t is equal to 0, what we discussed that For example, in the case where a simple single degree of freedom system which represented either a vehicle or a crane, the sudden disturbance in terms of either initial velocity or initial displacement that happened instantaneously at t is equal to 0. Okay. So, in this particular example, the initial displacement of the mass happened at exactly t is equal to 0 or at an instant of time from which the vibration response is to be obtained. So, there was what we can say that as a step change in the conditions, whereas when such excitation happens over a reasonable period of time, it is not an instantaneous excitation that we are talking about, but excitation taking for some short duration. Okay. Now, later on when we explore the response to a continuous forcing function f of t which appear on the right hand side of the governing equation of motion, we are going to explore the response to such a continuous excitation function separately. But what we are now going to discuss is when the excitation is not acting like an initial excitation or initial disturbance, and neither it is a sustained excitation over a long period of time. When such excitation exists, we call that excitation as a transient excitation, which excites the system for a short duration. Okay. In addition, the excitation can be arbitrary in the sense that we may not be able to mathematically define that excitation. In such cases, the treatment of finding out the response to a transient excitation can be adapted to take into account the response estimation for an arbitrary excitation, and we will discuss a little bit of that in this particular topic. Okay. So, in a sense what we are going to look at is a same governing equation of motion for a simple single degree of freedom system. Now that the right hand side is not going to be 0, but it will have certain time based function, and that time based function is not a sustained continuously occurring excitation function, but is going to be limited for a short duration. When that happens, how do we find the response is what we are supposed to discuss. Okay. The response of course is calculated using what is known as a convolution integral, also called by or is known as a Duhamel's integral, the scientist who proposed this integral. Now, what we do, we since the forcing function is can be arbitrary and will be a short duration, we treat this function as a piecewise linear function. What do we actually mean by that? That supposing a simple single degree of freedom system is subjected to a sudden force, okay, that force is a transient force acting for a duration from t is equal to 0 to t is equal to capital T, right. And not only that, but the value of this force at each instant of time may not follow a specific mathematical form, and therefore, we may not be able to express f of t as a function of time in the form of a simple standard mathematical functions. It can be arbitrary as we discussed. So, this variation is what we say is arbitrary. So, what we are going to assume here is that this transient arbitrary excitation function comprises of short duration excitations having a value which is treated as a constant value here. Okay. So, this force will have a value of let us say F1 at t is equal to 0 and will last for a short duration, which I may call that as delta T1. Okay. Now, a finite force acting for an extremely short duration of delta T1 is going to act like an impulse on the mass. Okay. So, this force variation, which is going to last for a period of capital T, is now going to be discretized into a series of short duration impulses acting on the system one after the other. So, in a way I can show this to be a set of such constant amplitude force acting for very short duration of time acting one after the other will make up the original force which is varying a bit arbitrarily, right. So, this is how all these impulses would look like, and they will all make up together as an original arbitrary forcing function as a function of time. So, the original arbitrary function is now replaced with these solitary impulses acting one after the other on the vibratory system, and investigating the response of these impulsive excitation is what we should be focusing on now. It is not necessary that the width or the time duration for this force to act should be identical throughout the span. So, if I want, I can approximate it with a varying time interval, and it can have impulses which could be of varying time interval. But the point is, if you have a too large a force duration, then it might approximate the arbitrary function and the accuracy obtained may be compromised. So, if possible we are expected to discretize this into a shorter duration excitations and then find out the total response, assuming each of these excitations acting one after the other. So, the assumption here is we treat the vibratory system to be linear and assume that this impulse is acting independent of all other impulses. Okay. So, all these impulses which are acting on the system one after the other are actually individual independent excitations to the system, and the subsequent excitation impulses are not dependent on the past history or what follows after it as well. Okay. And what we are also going to assume here is the total response is going to be summation of all these impulses acting on the system, and therefore, the linearity assumption here is going to be the mainstay of the evaluation process. We assume that the system is linear, and therefore, all of these separate impulses can be treated individually and separately, and the total response will be linear summation or superposition of the responses due to individual impulses. So, the assumption that we are going to use here in getting the response is that the system is linear, and linear superposition of all these individual impulse related responses are simply algebraically added together. Okay, with this background now, let us focus and understand how do I find the response of a simple single degree of freedom system to a solitary impulse which has a strength I, and we all know that is given by the force time the the time for which the force acts. Okay. So, if this time period is a small time period dt and the value of this force is f, the impulse is going to be f times dt, and then suppose such an impulse act on the system, what is going to be the ensuing vibration response. If we find out this response, then we will see as to how any other impulse later on, how that response is obtained, and then as we have discussed, the total response is going to be the linear superposition or linear addition of the responses of the subsequent impulses. Of course, what we have to ensure that the response of this impulse is going to start from here, whereas the response of this impulse is going to start from here. So, there would be response to this impulse going to begin like this will start from here, this will the response to this impulse will start from here, and so on. So, all of these will be added together to get the total response. That is the whole philosophy of finding out the response to a transient excitation. The examples of such excitations are many, and what I am just highlighting here are some of the practical examples. In case of a forging hammer, we I think discussed this example earlier, that if a top or a hammer falls from a height, that typically happens on a workpiece which is here mounted on the anvil, and then when this top or the hammer falls on the workpiece being forged, there will be a sudden excitation force acting on the workpiece and therefore on the anvil, and of course therefore on the total structure here, which is of course isolated or mounted using appropriate mounts on a large concrete bed, as you see here. So, if we want to find out how the force is going to impart vibratory motion to this particular body, we would be keen on understanding how that is to be done. So, the force which is going to act on this is going to be quite sudden, but that force itself can be found through some sensors and force measuring devices, but we may assume that suppose suddenly the force value will increase to a large value, and then as the workpiece gets compressed and forged into a piece, of course the force amplitude will reduce, and after the entire energy is absorbed, there will be no further excitation on the anvil. So, we may consider this to be the energy imparted to the workpiece by the falling hammer, and maybe the force time history for such a transient excitation will be given by this force variation. Okay. So, our objective will probably be to find out that after the hammer falls on the anvil, then how the anvil reacts to that in terms of its own vibratory motion. Okay. The other example could be some a blast loading force or a wind loading force on a tank like this. So, we may treat this tank to be a simple single degree of freedom system, maybe a mass at the top, and all these frame structure might be represented by some stiffness, and of course, that stiffness is going to be the bending stiffness of this entire structure, and the mass of the tank can be lumped at the top, and that is how we can treat this to be a simple single degree of freedom system. So, if I consider the overhead tank structure to be a simplified vibratory model like this, with the column structure represented as a simple beam, and then a mass sitting at the top, and then a force acting on it as a transient excitation. Maybe a blast pressure can act on it, which is generally modeled like a sudden increase in the force value and then an exponential decay in its value. So, this is a typical way in which a blast pressure act on as the blast happens, and we may have to now treat this as an excitation function. We may be able to capture that excitation function in the form of some mathematical function, but sometimes we may have to resort to the kind of small impulses we treated as individual constant amplitude impulses acting one after the other. So, this is another example how the excitation to a simple vibratory system can happen, and that the period for which this happens or period for which this acts is typically a small duration, and therefore, it is not sustained after a certain period of time, and therefore, we call this as a transient excitation. Many times short duration needs little clarification. Typically what we mean by short duration is that the period for which it acts is quite small as compared to the time period of oscillation of a vibratory system. So, for example, if we have a vibratory system whose time period of oscillation is, let us say, 1 second as an example. So, the period of free vibration response, if it is 1 second, to qualify the short duration transient, this t is typically should be a fraction of this 1 second. So, maybe 0.1 seconds, 100 milliseconds or less, and then that would ideally be treated like a sudden or a transient excitation. But it can go on even beyond that, provided the total excitation is treated appropriately. For example, I can treat the total excitation to be discretized into small duration impulsive excitations, and then for a longer duration also it can be investigated. So, as we discussed that it is going to be treated like a series of short duration excitations. So, it is almost like the mass is being subjected to a short duration impulse as it is shown here. So, we assume that the amplitude of the force does not change in that short period of time delta t. Then what effect will this force and the impulse have on the mass? Okay. So, the impulse value we all know is given by f cap into dt, if this is the time duration for which it has occurred. So, the impulse is equal to f cap dt, and we all know that this impulse will cause what? Will cause a change in the momentum. Okay. So, what change in the momentum will it cause? Okay. The change in the momentum will be given by v minus v naught. V naught is the initial velocity. Okay. Or I can write this as you can write this as m delta v, or if v naught is assumed 0. So, initial velocity is assumed 0. So, before the application of this impulse, if the initial condition at the start of this impulse is that x naught is equal to 0 and v naught is equal to 0, then in that case I is going to be m into v, where v is the velocity at this point. The impulse causes change in the velocity, that change in the velocity will be the velocity at the end of the impulse, and then this is equal to m into v. Now, that itself is equal to what? F cap dt. Okay. So, or v is written here as x naught dot, that is one and the same thing. So, I can get the expression for this velocity, which is the velocity that I get as f cap dt over m. Okay. So, I have the value of the velocity after the impulse ends as the initial condition for the system to vibrate. Now, imagine that there is no other excitation except this single impulse. Okay. So, to a vibratory model, if I ignore the damping to start with, what I am interested in is if the impulse acts on this mass, what is the ensuing vibration response. Now, we know very well that if I know what is the velocity imparted to this mass as an initial condition at t is equal to 0, what would be the response? We all have, if you remember, we obtained the expression x cos omega n t minus phi I. This is the expression that we derived for an undamped single degree of freedom vibratory system. Now, for which capital X, if you recollect, is what? X naught square plus V naught by omega n square cos omega n t minus phi I, where phi I is the initial phase lag, which is tan inverse of V naught over x naught into omega n. These are the expressions we already have derived for a single degree of freedom system for the initial conditions x naught and V naught. Now, just before the start of the impulse, we assumed these conditions existed. At the end of this short duration excitation in the form of this step impulse, the value of x naught can be presumed same, but velocity gets changed to this value. So, by application of an impulse of the value f cap dt, the value of the velocity exactly at the end of this impulse in a very fraction of a time changes to v, which is given here. Now, this itself I can treat as initial condition. Okay. What I will do is I will treat that as an initial condition to figure out what should be my response after the impulse ends. So, to do that, x t can be written as, now just have a look at this particular expression, my value of x naught is 0, is not it? Value of x naught is 0, value of v naught is this expression. So, ultimately this capital X which you see here, x naught being 0 and v naught by omega n as f cap dt. So, v naught over omega n cos omega n t minus phi I, v naught is this value f cap dt over m and omega n is already there. What is phi I? Now, make a note here, is dependent on v naught and x naught. Now, we have assumed x naught to be 0. So, which gives us the value of phi I to be 90 degrees, which of course makes this expression change to sin omega n t, phi I being 90 or pi by 2. So, the response of the system after the impulse ends is given by this expression. All right. Finer the dt value, larger is the amplitude, because this value is your amplitude. For the same f cap, if you reduce that delta t, amplitude will rise, larger you take it will reduce, and so that is how the response can be obtained for a solitary impulse. And it is important that what we have assumed, that we are going to use these impulses one after the other, okay, of different amplitude f to represent an arbitrary excitation function. this is what we have obtained, and this is what the exact expression that we have already derived. So, that basically is the response expression x t if the system is subjected to a solitary impulse. Now, how the response will look like, because it is a sinusoidal function, I mean the amplitude is f cap dt over m omega n, but the response will follow a sine curve, and that is why you can see that it is this whole response is with constant amplitude and with the natural frequency omega n. Damping is ignored in this case, and therefore, it will happen at omega n, and this is how it will oscillate. Now, the question is this impulse what we have seen happens at t is equal to 0. So, assuming a very small delta t, does not matter whether we treat this as t is equal to 0 or this as t is equal to 0. Okay. So, you can always assume it to be happening like that, but you remember that in an arbitrary case like this, what we initially decided that we will take care of this continuously varying excitation function as a set of constant amplitude impulses applied one after the other. So, later on we might be required to figure out what is the response to an impulse which is not at t is equal to 0 in a global time variable here. It will happen at a certain other time, maybe I will position this impulse at tau period, okay, or time tau seconds. So, we need to somehow modify this response expression to account for a different location of this impulse in time axis. So, before we do that, maybe it is interesting here to consider this response expression to be f convolved with this particular function, which is 1 over m omega n sin omega n t. So, this is called as unit impulse response function, where f is f cap dt as you know the impulse value, the amplitude of the impulse. So, this obviously is a unit impulse response function for the reason that if it is multiplied with the actual amplitude of the impulse or the strength of the impulse, what you get is the corresponding response to an impulse having a value of f cap dt. So, this can be written as f times h of t. H of t itself is the unit impulse response function. 1 over m omega n sin omega n t is the unit impulse response function for a single degree of freedom system. Yeah. So, if I the impulse value is 1, the response will be same as the unit impulse response function, right. So, this is basic stuff that you might need to know. Okay, in this lecture we discussed the geared rotor system, and this is the simple question that you can attempt just to recollect the concepts learned in the geared rotor case and try and verify your answer given in the next slide. What we discussed in this lecture is how a gear pair in a vibratory system is modeled or can be included in the model of a vibratory system. In that context, although the gear pair can be also accounted for by looking at the forces on each of the gears, but in this case we focused on the energy based method. So, how for calculating the energy, how the equivalent inertia or equivalent stiffness of a gear pair is included in getting the vibratory model. And we had a initial discussion on how an arbitrary excitation can be broken down into several impulses, and the response to a an individual impulse can be obtained, so that we can finally get the total response considering these impulses to be applied one after the other.